Hi everyone, happy to be here. Thank you for the introduction. So today I want to take you all beyond text and explore the possibilities of large multimodal models. So very quickly, what I'm going to talk about, I'm going to start with an introduction. So when I say a large multimodal model, everyone knows what I'm talking about. Next, I'll dive into a subset of these types of models called vision language models and see how they perform in the wild. And then finally, some more in-depth analysis about these models and, of course, a conclusion, some takeaways you can all take home. So let's dive straight in. So the goal in the next couple of minutes is that you will know what a large multimodal model is and, more importantly, when to use it. So a large model, large here means numbers of parameters of the models. So millions or even billions of parameters, scale of GPT type models. And then multimodal pertains to multiple input modalities. So here you can see some examples, text, images, video, audio. But for today specifically, I want to focus on multimodal models that take two input modalities, text and images. And these models are also referred to as vision language models, or VLMs. I've given this presentation in the past in Ghent and Berlin, and I always like to do a quick poll. By raise of hands, who here has used a large language model in a project of theirs? Yeah, most people. Okay, now who here has used a vision language model in one of their projects? Yeah. Still already a lot less people, and that's not surprising. I find this interesting visual from Landing AI, which basically shows that the vision revolution is trailing the text revolution. If you look at the start of these timelines, for example, the Transformers paper, only multiple years later, the vision transformer paper popped up. And we see a similar trend where something first pops up in the language, in the text domain, but then only later comes to the vision domain. So again, it's not a surprise that these things are only now starting to get used. But for me, that's really exciting. I'm a computer vision engineer, so for me it got exciting when vision got involved. So in the most simple sense, a vision language model, you have your two input modalities, text being your prompt, in this case, what is happening in the image, and of course the image itself, and then your output would be a man and a woman are cross-country skiing with their dog. Very simple example. For today, I don't want to dive into the technical details or the insights of these vision language models, but there is one technical detail that I do want to share, because it will come back later, it has quite some importance. And that is, we have a multimodal model, there's multiple information modalities, and you need to somehow combine that information. In general, there's 4 strategies to fuse your information. On the left-hand side, we have early fusion. Here, in the example, you have your text and your images modality. They get combined right from the start, and then you have a joint model that works on the joint representation of these two modalities. Then on the other side, if you look at the right-hand side, late fusion, that's the opposite. Here, there's an individual model for your text, in parallel, an individual model for your images, and only once you have processed that, the information is combined. Then there's also in the middle intermediate fusion. Here you have individual models, text go to the text model, images through the image model, combine it, and it still goes through a joint model. And yeah, finally, there's a 4th strategy, hybrid fusion, where if, for example, you have 3 modalities, you can use a certain strategy for 2, and then for a combination of other 2 another strategy. So there's combinations possible. The vision language models I'm going to talk about today all mainly employ a late fusion strategy. And why that is important, I'll get back to that at the end of the presentation. So let's dive in, vision language models, how do they perform in the wild? I'm going to talk about 3 models in particular, Gemini 1.5 Pro Vision from Google, GPT-4o from OpenAI, and Claude 3.5 from Anthropic. You can see the release dates. Gemini was released earlier this year, but the other 2 are still fairly recent. Again, these vision advancements are very recent and rapidly evolving as well. There are some differences in terms of the amount of input tokens, so your context window. The modalities that they take as input are more or less the same, but in this case, they take text and images. Image size, so the maximum resolution these models can deal with. That's also quite important detail, and there are some differences there. And then finally, the pricing. They all like to use their own pricing strategy. They do not agree on how to calculate the price for a certain image, so use their calculators to figure out for your use case what would be the price. But generally, I would say it's quite cheap. So let's dive straight into some examples. This is a use case we actually have in production at the moment for one of our clients. And you have food and beverage labels. These contain a lot of information, allergens, nutritional information, contact details, barcodes, and so on. And that information is typically jam-packed, close together in some creative way, so there is a very minor level of reasoning needed to extract the information. And so in this simplified example, my prompt is how much energy, salt, and fats are in this product per 100 grams, because it's in there for multiple weights, and provide the result as JSON. And this is not rocket science, so Gemini 1.5, no issue at all, gives me a nice JSON structured answer with that information. Okay, great, no big surprise. But then if we look at GPT-4o, here again, confident JSON format gives me an answer, but the amount of calories is just wrong. That's annoying, again, not rocket science. Why is it already making a mistake here? But then remember this slide. They all have a different max image resolution, and for GPT-4o, it's smaller compared to Gemini. So what actually happened, this was a very large image, and the text became unreadable after downscaling, so the model could not properly read it. So let's test that hypothesis. Let's zoom in, let's crop out the text, feed that to GPT-4o, and now, indeed, we get the correct amount of calories. Same happens for Claude. Same prompt, again, makes a mistake here in terms of salt, again, because of the image resolution. Let's crop, zoom in, no problem. We'll get it out there. So very interesting, and as I said, this is something we're currently using and works really well. All right, let's try to give it something a bit more complicated. This is a TV remote manual, so it contains some visuals, some text that explains how you can achieve certain functionality with your remote. In this case, my prompt is, how do I watch channel 54-3 with stereo audio? It's a certain specific channel. GPT-4o, not a problem at all. It gives me a step-by-step instructions on, okay, first press this button, then press that button, then do this to achieve what you want. Very nice. Same for Gemini. In general, I noticed Gemini does not really like to talk that much. It always gives very short answers. They're correct answers, but they're just very to the point, very short. But in this case, again, correct answer tells you what to do to achieve what you want. And then finally, same for Claude 3.5. Again, a bit more text, but gives you some nice steps on how you can achieve what you want. So this is a simple example of a single page from a manual, but think about use cases where you have hundreds or even thousands of pages long manuals, and people ask you questions. The answer is somewhere in that manual, but nobody wants to read the entire thing. Just feed it into one of these models. It can understand both the text and the visuals in there and can provide you with an answer, which is something really powerful, in my opinion. Something else I wanted to test is, okay, so this is a manual, there's text, there's images, it can answer my questions, but does it have some sense of domain knowledge? So in this case, in the manufacturing industry, the manufacturing domain, so I provide it with an image of a wooden plank at some stage in the production process, and I ask, in a manufacturing context, which defects are present in this image and how likely are they? My prompt is very simple. There's no prompt engineering here, so the answer is a bit all over the place, but it's correct. And it clearly shows that GPT-4o has some understanding of common defects in wood manufacturing. It mentions knots, there could be warping, rough sawing, variations in color and grain, splitting, and so on. So that's interesting. Clearly, it understands the process, and I have not given it any information other than this simple prompt and the image. Same applies to Gemini. Again, a bit shorter answer, but it understands the wood manufacturing process and can give me common issues that might occur. Same for Claude, lists a lot of potential things that could happen. So again, very interesting, simple use case, but it shows that it already has some domain knowledge. And it's similar for a lot of healthcare use cases. These models out of the box actually already know a lot about common diseases and things like that. So that's interesting. And then I thought, okay, let's test the limits of these models. So I looked online to find some sort of puzzle or riddle. So in this case, we have 4 images, 4 houses from Alex, Ben, Rick, and Maria. And the question is, there was a theft on a snowy day, but everyone claimed that they were home. One of them was lying. Who's the thief? By raise of hands, who knows the answer to this riddle? I see 1 person, 2. Okay, not a lot. No worries. I'll give you the answer. It's Rick that was the thief, and you can see it by looking at the snow under the car. Alex, Ben, and Maria, they don't have snow under their car. Rick does have snow under the car, which indicates that he was lying, that he was home because the car must have moved in order for snow to be there. So that's the answer. You can already see not everyone here figured it out. Maybe if I gave you a bit more time, you would have figured it out, of course. But I wondered, okay, GPT-4o, will it be able to give me the answer? Fortunately, not. It says, Alex is the thief, and I was really surprised by the complete nonsense of an explanation it gave me. It mentioned something about the entire driveway being clear of snow and some other things that are just completely not true. It just picks an answer and then comes up with whatever it wants to back that answer. Okay, no problem. There's still 2 other models we can try. Gemini thought, okay, yeah, let's go for Maria. Again, wrong. Gives an explanation. The snow on her car is undisturbed. Not true at all. Just comes up with some nonsense explanation for this wrong answer. But fear not, 1 more model. Let's pick the final person that is not the thief. Accuse that one, and again, come up with some nonsense explanation as to why this person was the thief. So this to me was quite disappointing, and you may think, okay, these models, they simply cannot solve this type of problem. This is not what they were made for. But as I said, I've given this talk in the past, and then I used GPT-4 Vision, so the predecessor of GPT-4o, and GPT-4 Vision was actually perfectly able to solve the riddle and actually gave an explanation that made sense, talking about the snow under the car. So OpenAI did something that somehow made it worse at this riddle. But so just to show, it is possible to solve these kinds of problems. And for me, the main learning here is it will always give you an answer. It will be very confident in its answer, and it will just come up with whatever explanation. So that's something you really need to be mindful about, that don't just believe what comes out, but I think most people, of course, know that. All right, so those were just a few examples. There's a lot more, of course, a lot of interesting learnings as well, but yeah, in the interest of time, I cannot share them all here today. But I wanted to do a bit more in-depth analysis and get to some conclusions about these models and when you would use such a vision language model. So this is from a paper called Vision Language Models Are Blind, and it's a quote from their paper, VLMs are dumber than a 5-year-old. In this case, we give all of these models 2 lines, a blue and a red line, and they might be intersecting multiple times or not. The question is, how many times do the blue and red lines touch each other? Answer with a number in curly brackets. This is something a 5-year-old can tell you. It's a very simple visual thing. Everyone here can look at these images and give the correct answer. But it's quite surprising that all of these models really struggle with this. As you can see at the results, sometimes they are correct, but I would say it's more of random luck rather than it actually understanding and reasoning about the image. So that's interesting. Another thing, more general, VLMs are bad at spatial reasoning, just altogether. Here, there's 2 circles and they might be overlapping. The question is, are the 2 circles overlapping? Answer with yes or no. again, they really struggle. There's not a single model that sort of gets correct answers across the line. Only like the example on the right, when there's a bit more separation between them, then it actually, most of them say no, the circles are not overlapping. But again, very interesting example. For us, this is very simple, but these large, complex models somehow cannot do this. Counting, another thing they are bad at. Here, we present it with a number of circles. In the first example, it's the Olympic symbol or the Olympic logo, which has 5 circles. 2 models get the correct answer, but then we add more and more circles, and just the answers are all over the place, just incorrect. Interestingly, if you look at the answers from Gemini 1.5, you'll see, so okay, first image, Olympic logo, 5 circles, I know this, 5. Add more circles, no problem, still 5. Add more, still 5. Change things around, still 5. So you can see there's something going on. It recognizes that Olympic logo, and even if we add some more stuff to it, it's still like, okay, no, I know this, say no more, 5. But just wrong. And in the paper, they actually give a very good explanation as to why these things occur, why it struggles with these things. And they say, because of not looking at the prompt while extracting visual features, VLMs might be blind to some low-level details, causing intelligent language models to struggle and sometimes make educated guesses. So let's look at that. The first part, because of not looking at the prompt while extracting visual features. Remember this slide. I said all of these models use some version of late fusion. And not looking at the prompt while extracting visual features, if you look at this, it makes sense. You have your prompt. Without knowing the image, it will process your prompt that goes to your text model. Then in parallel, completely independent, you have your image model, goes through that model, extracts features without knowing the prompt. And then only once you've processed all these things, that information is combined. But what happens in these examples, some very minor rudimentary visual features like intersecting lines or overlapping circles, that's simply just not extracted by your image model. So you give some visual features, you give some textual information from your prompt, but the information is not there to get to an answer. So it really struggles with that. So in the paper, they experimented with early fusion versions, and there they showed this is actually better. So I expect to see some advances there to solve these kinds of problems. So in conclusion, be mindful when using a VLM. Some of the upsides of these models, it's capable of very complex reasoning and visual understanding. There's a lot of complex use cases with visuals and text, and it can really reason about it and give you an answer, much better than some OCR and layout model combination can typically do. It contains a lot of domain knowledge. So I showed the manufacturing example, but as I said, healthcare use cases and plenty of other industries, it has some knowledge already, which is very powerful and very interesting. But of course, there's downsides. There's difficulty with small text, spatial reasoning, counting, as I've shown. So of course, if you have a use case where you want to count coins with these models, first of all, why would you use this model to count coins? But that aside, that's not going to work. So really think about what is your use case? What do you need the model to extract from your information? And is it actually capable of doing so? And also remember image resolution. As I showed in the beginning, it will just hallucinate, give you nonsense if it gets downscaled too much and you lose the information you actually need. And yeah, in general, the hallucinations, remember the riddle. There were 4 people, only 1 answer was correct, and the 3 models all picked the wrong person. So again, you need some sort of guardrails or supervision. So my advice is, when would you use these models? For complex multimodal reasoning, where a textual response is sufficient, important, because the output you get is still text, with human supervision or strict guardrails. So the use case that we had in the beginning with the food and beverage artworks, that's an example where we have very strict guardrails to make sure that the output is correct. So important, think about those things. All right, that's what I wanted to share. I hope you now know what a large multimodal is and when to use it. Thank you for your attention.